Hey, Wama, how we doing? Just good. Yeah. Hey, how many school gyms right now are getting ready to talk to an astronaut on the space station? One. You're off by one. Hey. Okay. Welcome to the ARIS Contact Day. It's been a long time coming, been a lot of work by a lot of people to put this together. So thank you to the students that submitted questions, the 15 students that got selected. Thank you to all of you who participated in the various opportunities that your teachers put together for you to learn about this opportunity. Thank you to all of you who put forth a question, and we appreciate you putting that out there, and that's awesome. And thank you, of course, all for being here. But I'd also like to thank all the people that actually made this event possible. Okay, from Mr. Brown over there, who started the whole process of applying to get us this great opportunity. We have Mr. Scannell working over there on the audio video system. He is our representative from ARIS. He's the one that helped us really make sure that all of this would come together and we put together well. We have our ham radio operators that are here today to help us out to make this happen. We're here last week setting up the radio on the roof. A big thanks to Pioneer Construction, who came out and got the equipment up on the roof of this gym so that we didn't have to make a human pyramid out of you guys to get it up there. Figured that was a better solution, right? And of course, we got to say thank you to NASA for giving us the opportunity to use the time of one of their astronauts on the space station. You'll see here in a little bit, one of your fellow aviators did a little math to figure out what you'd have to pay if you wanted to pay for 10 minutes of this astronaut's time. So it's a pretty big contribution to you and to your education that we get to participate in today. So here's what we're going to do. Our contact begins at about 2:20. And if you look, those of you that can see it on the wall over there, way back there on the wall, is a screen that shows the ground track of the International Space Station right now. And around that ground track, around that icon of the space station, is kind of an oblate circle, a green blob-looking thing. And if you're inside that blob, you have line of sight to the International Space Station. So we're looking to start talking, basically, as soon as Grand Rapids is inside that little green circle. So you can keep an eye on it over there as we work our way through our prep to make sure that we're on. And of course, this team over here, this wonderful team over here with the ham radio and all the equipment, which they'll explain to you in a few minutes, they're keeping an eye on it too to make sure that we get every possible second we can with the astronaut today. So we'll do we'll do a quick overview of the International Space Station, and an astronaut bio, Noah's going to come up and do that for us, and then we'll get a little brief into the equipment and what's working, how it's working, what's set up, and then we're going to hand it off to Grace Papay, who's actually the daughter of Doug Papay, who's going to give you the intro, and she's actually going to be the one to make the initial contact via radio with the space station. We get to use a kind of a cool call sign today. We get to use Whiskey 8 India Sierra Sierra, which is the same last letters, three last letters as the International Space Station, and we thank Mr. James French for letting us borrow his call sign so that we can do that. And then once we make the contact, we've got, hopefully all 15 students get a chance to do this, because we got to get all those contacts done before we leave that green blob up there on that screen, right? And as soon as we lose line of sight with the space station, we're done. So hopefully we get through all 15 questions. If time permits, if after the 15th question we have a few seconds, we're going to coordinate a real quick thank you for the astronaut. We'll just have you all yell thank you when we key the mic so we can hear you say thank you. And then we'll transition to a couple of other presentations on space flight and research stuff to kind of fill out the remainder of the assembly before we call it a day and go home. Okay, and right now I'm going to pass it off to Noah, who's going to give us a little talk about the space station. Here you go.
So yeah, as I said, I'm going to be talking to you guys about the International Space Station and also going to be going over the actual astronaut, or Najmana as you would call him in the UAE, and who we're going to be talking to today. So, I have to control my own slides, don't I?
I can do it for you if you'd like.
There you go. Yep, I can do it.
Cool.
Thank you. So the International Space Station, it's provided the ability for many countries to collaborate. It's used for things like research, collaboration. It's been a part of things like NASA, CSA, the Canadian Space Agency, the European Space Agency, Roscosmos, and it's just kind of provided the entire world the ability to do these kinds of things in space and kind of research that you can't really do on the Earth. So one thing that I always think is amazing and something that I always think about when it comes to the International Space Station is just how fast this thing is moving across our sky. Right now over there, you can actually read it over there if you can see it. It's currently traveling, I think, about 17,100 miles an hour, but for a good amount of time, and for the most part, it usually goes around the Earth at a speed of 17,500 miles per hour. If you really put that into perspective, that's around 5 miles per second, which is just, it's so much faster than anything that we see on the ground here at Earth. And to put that more into perspective, something like a trip to Traverse City, something like the seniors have seen if they're flying, it takes about 52 minutes for them to cruise in a Cessna 172 to Traverse City. In a car, it would take you about 2.5 hours, but in the ISS, it would only take you about 26 seconds. And about the time that I'm done giving you this presentation, it'll have traveled another 1,700 miles or so, or enough to get to Chicago to LA. So what exactly is the ISS for? Like I said, it's for, the biggest thing for it is research. It provides, it's virtually a floating laboratory in space, and it provides countries to collaborate on experiments, study experiments in microgravity and all kinds of things. It's also used as housing. You can live up there. Astronauts have things like air conditioning, they have kitchens, they have sleeping dorms and things like that. You really can do a lot of things. You can do a lot of things up in the ISS. So some examples of the research that they do up there. Life sciences, they do many studies on the human body and how space has affected the human body. They do things like sleep studies and sleep studies and testing certain medicines on the human body and seeing how microgravity can sort of affect that. Astronomy, something that I do here on Earth is study astronomy and kind of the sky, but when you're up in space, it really puts you a lot closer and gets you away from all the artificial light, and you really can see things up close. Meteorology, it really gives us a really good perspective on how to study the way that weather works down here in a way that you can't really observe down on the Earth. Materials, studying how space affects those materials that have been used to build the very ISS that is now up there now. Microgravity, obviously studying things in microgravity is something that you can't really do here. And of course, physics. Physics works differently in space than it works down here. There's just certain things that we can't really replicate here on Earth, but with things like the ISS, it allows not only the US, but the entire world to be able to use that kind of research and do that kind of research. So a bit of the timeline of the ISS, it officially started in 1998, which is when the US and Russia teamed up and docked the US module Unity and the Russian module Zarya, and that kind of made the start of the ISS. That was in 1998, and that couldn't really house any astronauts or cosmonauts, and that the astronauts were only put up there about 2 years later. And 2 years later, in 2000, the Zvezda module was connected, living quarters were first added, and the first crew arrived. Also in 2000, space shuttle missions, which were responsible for the majority of the construction of the ISS, started the ISS truss structure and the first set of solar arrays. And those solar arrays are going to be those large solar panels that you'll see on each side of the ISS. In 2002, you can see the space shuttles Discovery, Atlantis, and Endeavour will continue, more and more space shuttle missions will continue to build the ISS. However, in 2003, that was a big halt for the construction of the ISS, of course, with Columbia, they discovered many flaws with the space shuttle and the sort of dangers that came along with it. So it was paused until about 2005 or around 2006, where space shuttle returned with Atlantis and continued to build it. That first mission back was mainly to resupply astronauts and the second set of solar arrays. In 2009, the integrated truss system is completed, and the truss system is the big structure that was the building block of the ISS, and that is how everything is attached to the International Space Station. And in 2010 and to 2011, the space shuttle missions 130 through 133 mark the final missions to the ISS, adding the last of the module segments that we still have today. And this is just a little nice animation to show how each of these modules were added. You can see the truss structures going straight horizontally across and how all those things came together. You can look on this at your own time if you want. This is just on YouTube, and you can really see and dive deeper into how that played out. So in orbit, it orbits at an altitude of about 250 miles, and like I said, at a speed of 17,500 miles an hour. So when you look at that, the ISS will see about 16 sunrises and sunsets in, well, one day or 24 hours here on Earth. And you can see over on there, and you can see over on the screen over there, kind of the track of how the ISS travels in our sky. Now, one final thing is to know who we're speaking with today. The astronaut, or Najmanaut, that we're speaking with today, his name is Sultan Al Neyadi. He was launched with SpaceX Crew 6 this past March, and he is the United Arab Emirates' second Najmanaut into space. Najmanaut is just the term that you use for an astronaut from the UAE. So Sultan Neyadi, he's 41 years old. He worked as a network security engineer for the UAE's armed forces for about 20 years. And one thing that he always had while he worked there was a dream to become an astronaut. And that opportunity was opened to him in 2022 when it was opened up in 2018 when the UAE announced the opening for applications for sending UAE astronauts into space, which is something that that country has never seen before. Now, in 2022, he was selected for the United Arab Emirates' first long-term mission, which was the one that he was launched to with SpaceX Crew 6. Now, the thing about Neyadi's mission is that it really is historic. Not only is it the United Arab Emirates' first long-term mission to space, but it's their second Najmanaut at all. The first Najmanaut into space was in 2019, and the reason that it is significant that the UAE is now sending astronauts into space is because its founding father, Zayed Sultan Al Neyadi, some of those names are hard to pronounce. He always loved science, and he dreamed of his country going to space one day. And he never got to see that, but the fact that astronauts like Neyadi are now able to do that and are taking part in these first long-term missions and really getting into the ISS and working with other nations in space is just a huge milestone for the UAE and how these astronauts have been carrying on their legacy of their country that they have been wanting to achieve for the longest amount of time. That's about it.
All right, well, good afternoon. I'm Doug Pape, amateur radio call sign Kilo 8 Delta Papa, and I'm happy to be here with you guys. So we've got a few minutes before the space station is at the point of acquisition of signal, and I'm going to give you some quick comments here. I'm not going to go into a big presentation because we're all here to speak with an astronaut today, so we're going to do that. Over here we have an amateur radio station, and this is what we'll be using to make the contact today. This will be a direct contact meaning that we are not using any other technology in order to make this communication. We're using a radio frequency today and wireless communications. So this is kind of exciting for all of us. We're being streamed live on the internet, as well as I'm sure you'll be able to watch yourselves on TV later this evening. But we've got about 5 minutes or so. My daughter Grace, she's an amateur extra class operator, which is the top license, and she's her call sign is Kilo Echo 8 Radio Juliet Uniform. And I used radio there. I probably should use Romeo. I know you guys are all aviators here, so we use the correct phonetics. But she'll be initiating the contact. In order to do that, here just in a few moments, I'll hand the mic over to Grace, and she'll begin to call the station. As soon as we have acquisition of signal, and she has confirmed that our astronaut today is ready to take our questions, I'll take the microphone, and your fellow students will get to ask their questions. So pretty excited about that. If anyone's interested in amateur radio, if that sounds interesting after experiencing this today, there's several amateur radio operators here today from the American Radio Relay League, as well as some representing AMSAT, my daughter and myself, and Mike Waltheis. And we'll be happy to have a conversation with you. We'd really like to get you interested in amateur radio. We've got about, how many minutes, Grace? 5 minutes? Okay. So I'm going to step over by the computer here. The station is controlled by computer. We control both our antennas in azimuth and elevation, as well as our radio. The radio is Doppler controlled, and it is our responsibility here on the ground to transmit on a frequency that permits a constant frequency at the space station, in order that the space station crew does not have to adjust their radio. So we do all that work here on the ground. So just taking a look at the simulation here, or the predictions. The space station is currently 12 degrees below the horizon, so we're getting close. Once we're within a minute or so of acquisition of signal, Grace will begin to call.
We don't have, it hasn't turned green yet, huh? 2.5 minutes. Yeah, we're still a minute away, so more than a minute away. Just make sure that thing goes green and we see those antennas.
Maybe just say something like 1 minute away or 2 minutes away to see.
Okay. What are we at right now?
Okay, we're closing in on 2 minutes till acquisition of signal. The antenna system is programmed to begin tracking the space station here in just a few seconds. about 60 seconds before the space station is within view, the antennas will be into position, and we'll begin calling the station. So we're getting very close to acquisition of signal. Okay, the antennas are now moving into position, and once they're into position, I will hand the mic over to Grace, and she'll begin calling the station. Okay, the antennas are currently pointing west, and they're moving towards the northwest. The station will be approaching us from the northwest and go to the southeast. You ready?
November Alpha 1 Sierra Sierra, NA1SS. This is Whiskey 8 India Sierra Sierra, calling for a scheduled school contact. Over. November Alpha 1 Sierra Sierra, NA1SS. This is Whiskey 8 India Sierra Sierra, calling for a scheduled school contact. Over. November Alpha 1 Sierra Sierra, NA1SS. This is Whiskey 8 India Sierra Sierra for a scheduled school contact. Over. November Alpha 1 Sierra Sierra, NA1SS. This is Whiskey 8 India Sierra Sierra for a scheduled school contact. Over.
Hello, Whiskey 8 India Sierra Sierra. This is November Alpha 1 Sierra Sierra. Got you loud and clear. Over.
November Alpha 1 Sierra Sierra. This is Whiskey 8 India Sierra Sierra. You're 5x9 at the West Michigan Aviation Academy in Grand Rapids, Michigan. We have students, teachers, and many others here today. This is Grace, Golf, Romeo, Alpha, Charlie, Echo. I am the control operator for today's contact. Are you ready for the students' questions? Dr. Neyadi, over.
I'm ready for the event. Over.
Hello, my name is Caitlin, and I'm in 9th grade. How did you build and maintain the motivation to become an astronaut? Over.
Thank you for the question. Actually, I began motivated with reading throughout my high school and university time. So reading is the one weapon I would say that will be helping you throughout your preparation and becoming everything in space. So be it astronaut, engineer, or scientist. So reading is the most important thing for me. Over.
My name is Asta. I'm in 10th grade. My question is, what type of personal belongings and clothes do you bring to space and why?
Thank you, Asta. So my favorite thing is a jiu-jitsu kimono. Jiu-jitsu is a martial art, and I'm a practitioner. So I thought it's going to be fun for me to maybe wear that kimono and prepare some moves in space and see how it goes. So over.
My name is Janessa, and I'm in 9th grade. What kind of training do you get as an astronaut to mentally prepare you for the challenges of missions in space? Over.
Thank you for the question. So throughout the training, we actually do years of training. We do a lot of flying on the T-38 aircraft. We do hours of training in the MBA, which is the largest indoor pool in the world. So we simulate doing an EVA. Plus we do a lot of training in the ISS mock-up in Building 9 in Houston. So we spend a lot of years in training and preparation for a mission such as ours, which is 6 months long.
Hello, my name is Teague, and I'm in 9th grade. What are the hardest adjustments to living in space for long periods of time? Over.
Thank you, Teague. I think the hardest thing for me is seeing these rises, these mountains. So I remember arriving to the station and seeing that. I could not keep up with the timing. But luckily we have an international time, which is London Greenwich time, or mean time, that we keep as a reference when we do our daily jobs.
My name is Carter, and I'm in 11th grade. How has traveling to space affected your perspective on life and of the planet? Over.
I think, seeing Earth from a distance of 400 kilometers is really profound. So you see a thin layer of atmosphere that is protecting our valuable planet. So in that regard, we need to maintain the planet. We need to keep living in this beautiful planet without wasting the resources in meaningless stuff. Over.
My name is Eli, and I'm in 12th grade. Is it possible to get stuck in an open area of the space station where you cannot grab or push against anything to generate a force? If so, how do you get unstuck? Over.
Thanks, Eli. So there is a possibility, and only if we don't have ventilation running, which is very rare. So if you're in an open place, you just need to float, and ventilation will definitely send you somewhere around the station, to a wall, for example. But if you don't have that, you will definitely be stuck, so you have to yell for help from a friend. Over.
My name is Cooper, and I'm in 10th grade. Does electricity behave differently in orbit on the space station, and does it require any special precautions? Over.
Thank you, Cooper. So in the station we have two sections. The Russian segment, they use 28 volts of a source, and in the American segment or the U.S. segment we have 120. So in that regard, in every activity that we do, we need to make a lot of savings. So if we're dealing with an experiment that uses electricity, we need to use a saving mechanism to cut the electricity from that device. Plus we're wearing a static tether in case of a shock, so we have precautions before we do any activity. Over.
My name is Kira, and I'm in 10th grade. How do you deal with human waste and garbage on the space station? Over.
Thank you, Karen. So we have two types. The liquid type of waste, and we do recycle that. And well, luckily, because sending water to space is really expensive, really heavy, so we need to utilize a recycled water to purify that and reuse it. But unfortunately, the solid waste, we don't have a facility to reuse that, so we store them in barrels and send them to burn in atmosphere in a returning cargo vehicle. Over.
My name is Ray, and I'm in 11th grade. What kind of plant or animal research is being done on the space station? Over.
So historically, animals being used to test space vehicles. For example, the first living species that went to space is Laika, a Russian dog. But also some insects and animals were sent to space, and surprisingly, any animal that is capable of crawling on a wall, something they do very well. Unlike humans, that we only use a vertical means of walking, for example, on Earth. So currently we use plants to test other any sort of life form. So plants do well because we provide a lighting, we provide a ventilation. So we managed to harvest last month a few cherry tomatoes, which is very inspiring, and hopefully this will be a source of food in the future. Over.
My name is Isabel, and I'm in 12th grade. How does the lack of sunlight and gravity affect plant growth on the space station? Over.
Thank you, Isabel. So as I mentioned, we do use a special habitat that simulates different degrees of light, and we use ventilation and humidity according to a specific plant species. So as I mentioned, we managed to grow tomatoes, and we grow actually red pepper and so on. So it's in a test mode now, and hopefully in the future we can do more harvesting for different plants as well. Over.
My name is Patrick, and I'm in 10th grade. How do you prevent or respond to serious injuries in space? Over.
Thank you, Patrick. So as an astronaut, we train for years to deal with emergencies, and we are fully qualified to perform any emergency procedure on any crew members. So we have a full access to a pharmacy, for example, for any medication needed. So in that regard, we have the equipment to deal with any sort of emergency if needed. Over.
My name is Gavin. I'm in 10th grade. What personality or leadership traits is the space program looking for in astronaut candidates to be the best prepared to go on space missions? Over.
Thank you, Gavin. So personally, I think patience is the most attribute or let's say merit that anybody can have. So patience will get you through your examination, throughout your preparation, and will definitely make you persistence in seeking knowledge. And I do argue or urge you guys to seek STEM education, that is science, technology, engineering, mathematics. And with patience, you will definitely reach your goal. Over.
My name is Vivian and I'm in 10th grade. How is the mental health of the space station crew monitored? Over.
Yeah, luckily we have doctors that are tagging up with us every week. And just before talking to you guys, I talked to my doctor and they tag up with us, seeing our health and if we suffer from anything. And definitely working with a wonderful crew that the one that I have, it's really helping. So camaraderie and teammates are the best solution for any problem on board the station. Over.
My name is Megan and I'm in 9th grade. What subjects or lessons from your high school or college education do you apply most often on the space station? Over.
Thank you so much. So physics is the best subject for me when I was in high school, and I was eager to teach some students how physics work in microgravity. So I filmed some videos for students showing Newton law and how a moving object can continue moving without any problem on board the station because we are in microgravity. So it was really fun to apply some of the physics tricks that I learned as a student here on board the station. Over.
My name is Jaden and I'm in 10th grade. What are some things I can do now as a high school student to prepare me to become an astronaut? Thank you for your time. Over.
Yeah, thank you so much. Again, STEM education, and I think you guys, the school that you're in, the West Michigan Aviation Academy is the best place you can learn things. So science, technology, engineering, mathematics will definitely open up the doors for you guys to seek a career in space, for example. You can be an engineer, a scientist, an astronaut, or a researcher in space. So yeah, seek STEM. Over.
On behalf of everyone here at the West Michigan Aviation Academy, we would like to thank you for taking your time to answer the students' questions today. November Alpha 1 Sierra Sierra, Whiskey 8, India Sierra Sierra 7-3.
All right. That was pretty cool, right? What was the best part about that whole thing? Physics. Physics, right, Mr. Lewis? Physics. Yeah. All right. Great job to all of our students who asked questions. You guys did a wonderful job. Appreciate that. I'm now going to bring up Levi so he can tell us a little bit about the history of spaceflight.
Gemini. It was the second capsule to work on the ISS, and today we're going to take a deep dive into the missions that it wanted to achieve, the things that happened with it, and all the people that made it possible. First off, the project objectives. The main reason they wanted to do Gemini was, of course, to experience prolonged spaceflight. At this time, people had been in space, but not for very long periods, and NASA really wanted to study what would happen to things like bone density and muscle mass. Another one that they wanted to work on perfecting was space docking and re-entry. It was very new at the time for them to dock things in space, and on this mission, on one of the missions on Gemini, they actually docked for the first time with 2 spacecraft in low Earth orbit. Again, with re-entry, they wanted to work on that as they had an upgraded heat shield on this over the Mercury capsule. There was an extensive list of astronauts that worked both inside and outside of the Gemini capsule, but a few of those include Gus Grissom. Whoa. I am not doing that. Yeah, they're not. Maybe. Went to the end. I can go without them if you need. I memorized it. We're just cast people. Up, yeah. Wonderful.
There you go.
Oh, we're good.
There we go.
Thank you, Mr. Forney. Okay. Anyway, we'll get back to this. Some of those include Gus Grissom, Ed White, Wally Schirra, John Young, and Jim Lovell. All of these people worked on Gemini at least once. However, a few of them, as you can see, worked on Gemini on multiple missions. Now onto the actual capsule spacecraft. This capsule was almost a direct copy of the Mercury capsule. However, it was a little bit bigger to allow for more space because it was extraordinarily small and cramped for the astronauts, and a few of the things were repositioned. It ended up going on 12 different missions and was able to use those repositioned things such as water, oxygen, thrusters, and electrical power. The rockets that actually got it up there were all extremely powerful, and many of them were also used by the US Air Force. Titan II was originally a missile, but NASA thought they could repurpose it since it was strong enough to get the capsule up into space. The second one they used was the Atlas V, and that delivered classified payloads, satellites, and other capsules to space, and that was one of the ones that was used by the US Air Force. Another one was the Atlas Agena. This was derived from the SM-65 Atlas, and this was an incredibly powerful rocket, and they used it 109 times before retiring. The final one was the Titan IIIC. This was the most powerful of the four, and it had a large array of rocket motors on the bottom that allowed it to be the most powerful. This was also used by the US Air Force. On to the actual missions. Gemini 3 was the first mission manned by people. The first two were simply getting the craft up there and testing the basic systems, as number 3 was. Really just making sure the Gemini worked the way it was supposed to. Number 4 was to test the astronauts and the Gemini's actual capabilities. They wanted to see the limits that they could push this to and what they could do with the capsule. Number 5 was simply flying in space for 8 days. Spaceflight at this time was very short and often short-lived, and 8 days was an achievement for the Gemini capsule. Number 6 was also a long-duration flight as one of the main goals. 7 was also the same, but the main goal was to practice for future Apollo missions. Number 8 was a mission of firsts, as I'll go into later. This was the first docking of 2 spacecraft, and this was a monumental achievement for NASA. Number 9 was also the same thing, practicing those docking techniques, and 10 was, again, the same thing with the target Agena vehicle. As I said, Gemini 8 was a mission of firsts. The first being first docking. Putting 2 things together in space is obviously an incredibly hard task. Like they said, it has to be moving at an incredible rate of speed, and they have to match perfectly just so that nothing goes wrong. It was also the first abort mission NASA ever had in spaceflight in orbit. With that, they tried to dock 4 separate times, 3 of which were successful. The last one, there was a problem with the firing plugs, which caused them to have to abort and go back to Earth. Again, this was also the 6-man Gemini mission, which was an achievement for NASA because it showed how much they could do with Gemini and what they could do in the future. Of course, we have resources, and thank you all for listening, and please enjoy the next presentation.
I click to the right, correct?
Yep.
Thank you. Hi, my name is Carter, and I would talk to you about broadcasting with high-definition images. HD cameras in space, it's quite a new thing. NASA recently mounted some NTSC cameras in space on the ISS, and they use that based on their diagram of a 3-point truss system, and that allows them to move that camera freely throughout the ISS and create different angles. It also is used for civilian use in TV shows and commercials. A very famous example of this was actually the Pocari Sweat commercial. It was a Japanese sports drink brand, and it featured astronauts doing somersaults in space. Broadcasting, conventionally, HDTV, due to its high bandwidth, was forced to be brought down to Earth on return flights. But JAXA, or the Japanese Space Agency, is planning to implement a system that allows relay satellites and stations to broadcast it throughout the world and across various continents. A weird phenomenon, though, with the HD cameras, though, is that it has like white blips or flares in it due to the high resolution that wasn't seen in normal commercial-grade conventional cameras at the time. And so that was caused by, they believe, space radiation and just the high focus point of the cameras. So what they did to try to solve that is they did numerous experience in the irradiation of the cameras, of a CCD and CMOS cameras to help minimize those issues in the past. And so after that, they developed various types of those cameras to help conclude what the best camera would be useful on the space station for future research and commercial purposes. And in the future, the HDTV downlink system will be put into effect on the International Space Station. And the Japanese module Kibo will be put into place to help experiment further with higher definition cameras on the space station and help collect experiments and data. Thank you, everyone, and I hope you enjoy Gavin's presentation.
Hey everyone, somewhat obviously, I'm the last presentation, so you get to put up with me for a couple of minutes, and then you are good to go home. Sorry, false promises again. My slides aren't up.
What's that?
My slides up?
You got to use both hands.
Both hands?
You have twice as many as me.
Fine. Nice. So, we have 5 slides, okay? You're not putting up with me for too long. So, before anything else, this is the ISS. It's pretty cool. And I'm going to mainly be talking to you about why it orbits and why that map over there looks like that. For everyone who can't see the map over there, I have my own image, so don't worry, I care about my fellow classmates. So, before the orbits, before the fun, things moving in space very quickly, we get to do some math. Yay, math, woohoo, let's go. Anyway, I'll make it quick, don't worry. ISS cost about $150 billion, which is kind of a lot, but let's continue. It's been open to crew, as Noah mentioned. It's been open to crew since about November of 2000, which is 8,200 days ago. You can do some nice long division and get to a price of $18.3 million per day to put a person on the ISS is the value of their time. Or, $12,700 a minute, meaning that theoretically, if you wanted to pay for Dr. Al Neyadi's time based on the cost of the ISS, you'd pay him about over $100,000, which is kind of a lot, but we had fun, so it was worth it, right? Cool. $100,000 of taxpayer money, our fun, I'll take it. That's a trade I'll take every day of the week. So, now that's all the math, no more math, it's all graphics in space and satellites from here on out. So, the ISS orbits about 250 miles up above Earth's surface, which is about here to the Mackinac Bridge. So if you drive here to the Mackinac Bridge, it takes about 4 hours. You can turn that distance, here to the Mackinac Bridge, turn that up. The ISS is now 250 miles that way. Which kind of sounds like a long distance, 4 hours in a car, that's a while. But when you think about the fact that Earth is really big, it's actually not that far. Earth is 8,000 miles across, and we're only 200 miles up. So if you zoom out far enough, the ISS is actually pretty close to the Earth's surface on the scale of these things. And then as Noah mentioned, it's moving really, really quickly, which just makes that feeling of being far from the Earth diminish that much more because, I said I was out of math, so I can't actually do this calculation, but I imagine 200 miles feels a lot smaller when you're moving at 17,000 miles an hour. So, the famous map. It looks like this because of the way that the projection goes to... Oh no, my projection isn't here. Don't worry, I'll explain. So, the Earth has 3 dimensions, and this map is in 2 dimensions, so this sine wave just falls out of the fact that the ISS is not orbiting at the equator. It's actually orbiting at a 50-degree tilt. That's meant to be the next slide. And then you can just kind of see here, when it's at the northern parts of it, it's at the higher parts of that tilt. At the southern parts of that tilt, it's on the southern parts of the map. As for this behavior right here, where it goes, where it's in different spots every time, Earth is spinning, in case you weren't aware. Earth is spinning, and the ISS is not really spinning with the Earth. So Earth spins under the ISS. Earth is not in the same place as it was on the ISS's previous orbit. So then you get this map, and it's very pretty, and I like it a lot. That's 5 slides. Not sure if you were counting, but I'm done. Thank you.
So, I know that every one of you is super disappointed that you're not sitting in class right now. I know. But we still managed to learn something, right? We still managed to, we did something pretty cool. We managed to learn some pretty cool things, thanks to our student presenters, thanks to the students that asked some questions. Now we have a unique opportunity. We can no longer talk to the astronaut. Sultan Al Neyadi, Dr. Neyadi is, well, where is he now? He's, yeah, it's nighttime, almost nighttime. He's leaving South America right now, so we can't talk to him anymore. But we do still have a unique opportunity, right? We have all of these men and women over here who know an awful lot about amateur radio, about ham radio. You have all of the students that presented to you. So what do you want to know? We got a few minutes here. Anybody have any questions they want to ask about any of our presenters? Eli. What's that?
Could they repeat one more time who we talked to if we're interested in learning more about this stuff?
Yeah, absolutely. Mr. Pepe, you want to jump in here and help me out with that one?
Sure thing.
Thank you, sir.
Yeah, you're welcome. And maybe I'm on all the questions from this point on. We'll see. We'll see. I don't know about that. The astronaut that we spoke with today was.
If they're interested about radio, right?
Oh, you want to know about radio? Oh, well, you can talk to me. No, actually there are a lot of resources online. The first would be the ARRL.org. That's the National Association for Amateur Radio. And that's a great place to get started. There's a lot of information there, including information on licensing, as well as the many facets of amateur radio that you can actually participate in. So that's a good place to start. But local clubs are also a place to start. There's actually several local clubs in the Grand Rapids and West Michigan area. This particular event, we partnered with the Lowell Amateur Radio Club, LARC as it's known. Holland, where I'm a resident, has the Holland Amateur Radio Club, HARC, all nice acronyms. And there are several others, as well as the GRARA, which is the Grand Rapids Amateur Radio Association, WADC, right in Grand Rapids. Several others around, depending on where you live. You might be able to find a local club pretty close to you. And there's many individuals within those clubs that are excited to talk to you and give you a little more information on how to get started.
Okay. Thank you. I got the question. Good job. Okay. So Mr. Brown just volunteered to start a ham radio club here if you want to do that too.
Anybody's interested, I got a radio, we can get started.
What question did you have? About gravity in space? What's the question? Oh, you mean if, okay, I think in space it would go up, but I think you mean inside the space station, right? It's interesting, right? The flame that you're used to, the shape of the flame that you're used to, only exists because of gravity, right? Because gravity causes buoyancy, causes the warm air to rise, which gives the flame its shape. In the absence of, and it's not that there's no gravity up there, it's that everything is falling at the same rate. And since everything is falling at the same rate, you're not going to get the same kind of convection, kind of buoyant hot air. And so fire does some really cool things. It basically just makes little like pulsating globes of plasma in a compartment where it can burn. It's pretty amazing. You get on YouTube, you can actually find some pretty cool videos of it. It's pretty awesome. Good question. Anybody else? For building it? That's a great question for, who gave that? Noah. Where's Noah at? Noah, the question is, what kind of materials did they build the space station out of? Any idea? Honestly, no. All right, well, there you go. We got some more research that we can do, right? Some more things that we can learn. Great question, okay? Great question. Megan? No, yeah, I mean, that is not a question for me. I can tug that back to Mr. Pepe. Mr. Pepe, what do we do in radio clubs?
Okay, that's a great question. Radio clubs do quite a few things. Typically, it's a group of individuals who have a common interest, and they specifically are going to maybe first provide a service, perhaps a public service. So clubs oftentimes get together to participate in various events, such as the Tulip Time Parade in Holland. The Holland Amateur Radio Club supports that event by providing radio communications between various checkpoints and the medical teams that are on the ground, so we relay information. But clubs also get involved with other events like Field Day. That's an annual event that occurs in June, and that's a point at which we gather all our gear up and we try to build a station out in the field and establish emergency communications to demonstrate our capabilities. That's oftentimes done with technology like solar. We've used generators and other emergency power to do that. Clubs also get involved with supporting events like this, obviously, and they also are quite involved with technology, sharing technology. The Holland Amateur Radio Club has a session they call EAT, which is Education and Training, and that's hosted on a periodic basis where we cover topics on electronics and other radio-related topics. So there's a lot of things that clubs do, and each club has its own unique set of interests and capabilities.
Thank you. Yeah. All right. Unfortunately, I think we're going to, I appreciate another question. You can get us offline with any of the questions, but I think now it might be time that you're sick of hearing the sound of my voice. Some of you had to listen to me for over an hour talking about chemistry this morning too, so it's time to give you a break. I am going to call up WAMA's very own Mr. Pavey to bring us home. There you go. Stay here.
Okay, so Mr. Fortney asked me to close this thing out, bring some context to it for us at the school level and issue out some thank yous, which we kind of hit some thank yous to begin with, but to put it in context. Okay, most of you that have been in part of the aviation engineering department, we talk about three things: safety first, professionalism, and the pursuit of excellence. What you just saw, okay, was professionalism at the highest level. We couldn't be any more honored to see what you just saw, because this is what professionals do. They take something that's incredibly complex, incredibly hard, and they make it look easy. We just talked to the International Space Station due to these folks. That's a massive round of applause. I'll bet, because so like from a pilot's perspective, I'll bet they're all sitting there going, whew, I'm glad it worked. All right, sweet. Okay, the next piece of the puzzle. I want to thank everybody in the Sea of Blue. Okay, the Sea of Blue. Okay, your ladies and gentlemen, you rocked it today. I appreciate that. Okay, you're looking for the next right thing to do, and I appreciate your attention through this whole process. All right, keep up that good work. Okay, yeah, you don't get to give yourself an applause. All right. The next piece of the puzzle, all right? None of this happened. We did this about 5-6 years ago, okay? But it wasn't but for the vision and the forethought of Mr. Brown to apply and go through the process of getting us approved of this. This is an absolutely unique opportunity. This just doesn't happen in every high school. This is our second time. Thank you, Mr. Brown. All right, and so for my clock watchers out there, I still got 5 minutes, okay? I got 5 minutes. All right, I'll be done before the bell. All right? All right, my next one. Okay, so you get someone that gets it here, all right, but this stuff isn't magic. And it doesn't happen without a whole lot of effort and a whole lot of work. Okay, the execution, the coordination, all that stuff that makes it happen, I think you guys figured it out. This is your man. Round of applause. I will say though, okay, because this is his first real like leading the assemblies, that he missed one of our WAMA traditions that I just cannot go without. Join me in the pledge. I pledge allegiance to the flag
of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Okay, so I've got one last closeout, and then we're going to dismiss. Just so that you have it in your mind's eye how we're going to do this dismissal. It will be by grades. And guess who gets to go first? Guess who's going last? Okay, last context. This school has been around since 2010. Ask yourself where you were in 2010 if you're a student. Yeah, exactly. We're all about, all right, I got you. Check this out. All right, we're all about the aviation and engineering, the yin and yang of it all. Okay? Everybody sees aviation on the door, but there's an absolutely huge piece of this that is the engineering. And I'm here to tell you, if I could have Mr. Ron Baum stand up, okay? We don't have engineering without this man. And check this out. He's 76. When he was in 7th grade, Sputnik went up. And if you could imagine, I'll bet you, he's sitting there with immense pride that we have a school that for the second time has talked to the International Space Station. And what I would tell you this, I am absolutely certain, okay, that when I'm that age, one of you will be doing that to us. One of you will be up there calling down to us. That's my challenge to you. All right? Don't underestimate. Think about what our sayings here. Think about what this is. The higher the altitude, the broader your horizon. All right? Okay, so with that, a quick round of applause for last round of applause. All right, seniors, you're out of here. All right, juniors, you're out of here.